Okay, so the topic which we are going to study is generative modeling. There are two chapters in Bishop's book. One chapter is chapter 10, approximate inference, and the second chapter is chapter 11 on sampling. So these two chapters will be useful or will serve as the reference to do what we are going to do. Let me now give you a very uh, helicopter kind of understanding that what we are doing. Uh, so, as you know, distributions are very useful. Okay, so there are two lectures which will serve as prerequisite or good readings. So these chapters are on probability distributions, probability distribution, probability distribution, and there will be two videos which I will share from MLSP course, which are very basic concepts, basics of probability theory, that what are distributions, what are transformations of distributions, what are conditional distributions. So those very basic concepts, I'm not going to discuss them now, but I'll share those videos and you can just watch them, or if you have done MLSP course, then you have already gone through those parts. You can still watch those videos for refreshing those concepts. Okay, and now uh, what are probability distributions? So what we are going to do, okay, so what we have seen until now are classification and regression problems. So basically we have a model F, right? Given an X, you learn how to, so your F of X, you want to make it as close to your Y desired as possible, right? You want to make this approximately equal to, that you want to make these almost equal, right? That was your classification or regression problems. So if you remember soft classification as opposed to hard classification, what we said my f of x will basically be not just a scalar, but will be a distribution. This is the probability of y given x, right? And we want to maximize probability of y desired given x, right? This was my maximum likelihood kind of learning, where I want to say that my distribution, the output distribution is close to uh, what is called one hot vector, right? It peaks at the y desired. Let's say there are four classes possible: car, boy, girl, aeroplane. And if the input is a car, then my P will be high, P will be low, P will be low, P will be low. This is the probability of the class, right? If my given x, given the image, my probability of car is the highest. These are basically categorical distributions. It's called categorical distribution, right? Now, I think just to correlate with what we are saying, uh, so you remember now you saw the imbalanced data problem. So what you saw, for a particular class, there are very little number of samples available. So xi correspond to a particular class. Let's say the class is plane. For the aeroplane class, there are very less number of samples available. So let's say my X space is something like this, like X2, X1. It could be multidimensional, so it will be X3, X4 also. And let's say these are roughly my samples for one class. These are my samples for another class. These are my samples for another class. And these are my samples for another class, right? But let's say these samples are very less in number. So what I do, I can generate more samples. So how can I generate more samples? By sampling from the distribution of this class. Generate more samples by sampling from probability of X given plane. If my class is plane and I know this distribution, then I can sample from this distribution and I can get more examples of plane, right? And if this distribution is a perfect distribution, basically it perfectly has modeled all the planes, then I can get very valid samples of planes, right? So this is the utility of sampling more data. So the basic or yeah, the basic problem is how to estimate a distribution from where we can sample very easily. So um, how to sample efficiently from a given distribution P of X, right? Another problem is given samples, how to given samples X, how to estimate P of X and sample more X from it. Okay. Can you think of some possible uses of this in real life? Can you think of some possible uses? I told you one utility that in imbalanced data, you can do some sampling from these. You have, so the second problem, you have some samples. From there, you estimate P of X and then sample more data from this P of X, right? This was one utility. Another utility could be,
So deepfake,
pardon,
deepfake photos,
D.
fake.
No, I didn't get it. What is that? D.
So to replicate one's photos, which were not originally his.
Okay. Yeah. Yes. Very good. So, for example, you have a picture of Mona Lisa. There is only single Mona Lisa, and you want to make a video in which Mona Lisa is smiling or crying or showing different expressions, right? So if you learn that distribution, if you know, let's say if you look at any other person, you know how the face will transform if the person smiles or cries or shows different expressions. And learning those deformations or those transformations from there, you can apply it to Mona Lisa in a probabilistic way, and you can sample new images of Mona Lisa which are showing different emotions, right? So very good utility. So use number two is to generate new images or pics with different emotions, right? Anybody else?
So for many of the tasks, actually, we need a big data. So to create more and more data, let's say if we take the example of the numerous data set. So basically, I see people generating a lots of images of numbers, and then using some models.
Mm-hmm.
So basically, to generate a big data set from a small one
Hmm.
at a lower cost, basically.
Yeah, yeah, yeah. Yes. So that will be kind of utility one, where you want to have imbalanced data. So in your case, instead of imbalanced data, you are saying every class has small data. You want to upsample it.
Yeah, yes, sir.
Yes. Good. Any more utility?
Sir, can it be used for data augmentation like
Data augmentation I already discussed, like in use one, imbalanced data or small data.
So in some of the artistic pictures, it is that they have combined two pictures. Like one is providing the background and one is providing the landscape. So is that a part of this thing only? GAN.
Yeah. Yes, yes. To generate artistic images, it's similar to use two actually, but okay. Artistic images by combining different concepts. It's very much like the second use number two, but okay, fine. Any more utility?
So music generation.
Music generation is okay. Just like we are giving examples from picture generation, you can generate music, you can generate speech, you can generate any kind of data, sensor data,
Short short stories.
short story text data. Yeah, exactly. So these examples can you can move them from images to any domain.
So we can use it for security purposes. So basically, we can learn our distribution, the actual distribution of the data, and so we can know that what the real ones are and what the fake ones are. So
Okay, security purpose. Yes. So basically, you are generating fake images, uh, which are very similar to our true images, and in this way, you are imagining different distortions possible to the true image. For example, in fingerprint matching, if you can generate different fingerprints which look like my fingerprint, very similar to my fingerprint, but they are generated with a transformation which is sampled probabilistically, so that I know that this is not the true fingerprint. But my neural network, how does it know? My neural network can make a mistake. There is a good paper in this. Uh, Maybe I will share that paper. I'll bring up that paper in the next class. That how neural networks can be fooled by similar looking images or maybe very dissimilar looking images. Like if you show an image of just stripes, and the neural network says, "Oh, this is a starfish," or "This is a striped fish," right? Why? Because neural networks are basically uh, they divide the region, the entire space. They divide it into, with the help of boundaries, into many zones. So let us say this zone belongs to fish, this zone belongs to zebra, this belongs to some other category. Then there may be these valid fish samples here, but then let's say take a sample from here. This is not a fish, but still it is in that boundary, right? It is in that zone, but it is in the zone, in the fish zone. So my neural network will classify this point also as a fish, although it is not a fish. Just because neural network is a discriminative model, it learns the boundaries between different classes, but does not learn what is not a fish if that data is not provided, right? So that is why generative model can be used to generate fake fish images in this region, and then neural network can learn to construct a boundary like this. This is they're called adversarial images. Why adversarial? Because they look like, or the neural network does not know these are not fishes, right? Okay. Yes. So for security purpose, very good application. Another utility is, what could be another utility? Another utility could be to fill in missing values. For example, if I give you this image and I ask you what will come here, what will you say? If this portion is missing, what will come here?
Nose.
Yeah, you can easily say it will be something like this, right? Or it means you know it cannot be something like what do you say? I don't know. Maybe this still. Uh, it can't be something like, mm, right? This is very unlikely. This is likely, right? So how do you know this? You know this because you have seen so many pictures of people and nowhere you have seen, or for example, I can take another example. Just let's say uh, this is a person and I hide this portion. This portion is cut. And I ask you what is behind this? You will say it will be either hands, but it is very unlikely that you will get something like this. This is unlikely, right? So you know roughly the distribution, and from there you can learn to fill in missing values. For example, if you have the Mona Lisa picture and somebody takes away the nose of Mona Lisa and asks you, can you restore that image? So you will say, yeah, let me use my generative model. So in that case, it will be conditioned on the known values, and you are just estimating the missed values or missing values. So this is a very good utility of um, generative models. Any more use? Another utility is you are given p of x, and I ask you find expected value of x. Find expected value of x square. How will you do that? How will you do that? Or any expected value of any function of x. How will you do that? Right? How will you do that?
fx px integral over all x.
Yes, you will compute expected value of fx is equal to integral of px fx dx, right? And let us say this integral is very complicated to compute. Like px is a very complicated function, and fx could also be complicated or simple depending on your choice. But px is very complicated and you cannot solve it analytically. Not solvable analytically. Then what do you do? How will you estimate these values?
Sir,
Yeah.
I have a doubt actually. Let's say the x px is the probability distribution of x. So when we do some transformation, let's say fx, doesn't it the probability px should be changed?
No, px will not change. P of fx will be different.
Yes, sir. So should we not use like p of fx here rather than instead of p of x?
Mm, should we not use? No, then that will become something like this. Expected value of over z sampled from fx. Expected value of z. Something like this. But what we are saying is x. Actually, when I say expected value of fx, this is incomplete. I should say expected value of x sampled from px fx. Here also x sampled px
Okay.
square. Expected value of x sampled from px. Yeah, this is the proper notation. And if I simply say e of x, this is incomplete. And but it is kind of assumed that this is the this is what I mean, the default understanding. And but what you are saying is this expected value of z sampled from p of fx, something, some maybe some different q, some different distribution of fx, right? Yeah. Okay. So the answer is you may not be able to solve analytically, but what you can do is you can generate some samples. So the steps will be generate random samples of x and then compute sample average or sample variance or sample average or sample statistics over these samples, right? Let us say I will sample, let's say x1 comma x2 comma all these x capital N, all these are sampled from p of x. Then I will say my expected value of x, which was originally x px dx, this can be approximated as 1 upon capital N xs sum over all s, right? And similarly, expected value of f of x can be, this is very analytically intractable, but I can say this is 1 upon capital N so this is one way to approximate statistics for some random variable. If you know the distribution, if you can sample from that distribution, generate random samples of x from p of x, and then you compute sample statistics, right? In many cases, it is possible if, now the question is, uh, sometimes it is difficult to it is difficult to uh, sample from Px. Or sometimes it is difficult to sorry, sometimes Px is not given, but samples are given. So we have to first of all estimate Px and then sample from it. Means to get more samples, right? So um, okay. So let us come to the first problem. I think second one we have already discussed, so I will just remove it for the time being. This we have already seen before. I think this problem is interesting. Sometimes it is difficult to sample from Px because it's too complicated. So what we do is approximate. Therefore, the solution is approximate Px with some Qx, which is number one, close to Px, and number two, easy to sample. Yeah. Approximate Px with some Qx such that this Qx is close to Px and it is easy to sample. How do you find similarity between two distributions? Very quick question. How do you find similarity between two distributions?
Their correlation.
Correlation between two distributions. I don't think it is possible.
So we can take basic mean and variance, and we can take that particular distribution Qx, which has the same distribution as of Px, or maybe let's say mod, like which satisfies some basic properties of
Okay,
Px.
you are saying that here their statistics should match.
Yes, sir.
Yeah, that's a good approximation, a good try. But what statistics should match? If you just look at mean and variance, they may be same for two distributions, but then other things might be different, right? Two distributions may have same mean and variance, but the distributions themselves may not be same. Can we find a metric which uh, quantifies how different are two distributions or how same are two distributions?
Sir, can we take likelihood? Let's say we take M models, we take M distributions, and then we take the likelihood of each of these distributions, like how close these
Yeah,
distributions are to each other.
good try. What about likelihood? Likelihood works if we are given samples from Px and some Qx. So likelihood is for matching Qx and samples from Px. Right? You take these samples and put them in Qx and you try to maximize the probability. That is likelihood, right?
Yes, sir.
Likelihood approach. When you have samples from one distribution and an approximation of other distribution, and then you try to maximize the likelihood so that this Qx is very close to Px. Yeah, good try. But let us say now we are given Px, the distribution itself. Let's say it's a Gaussian distribution and Qx is a uniform distribution. And I'm trying to say, can you find which uniform distribution will be closest to this Gaussian distribution, right? Find out the appropriate value of mean and variance, or in this case, the width and the center of your uniform distribution. so that it closely matches with the Gaussian distribution.
KL divergence.
Yeah, yes, very good answer. KL divergence is one uh, distance metric which compares two distributions. So KL divergence is zero when Px and Qx are exactly same, and it becomes larger and larger as these two distributions become more and more dissimilar. There are other kind of measures also very similar to KL divergence, but yeah, KL divergence is, I think, very popular. Okay, with that, I think we can stop here. In the next class, we'll be discussing this thing. How do we approximate a complicated distribution Px with some simpler distribution, let's say Qx? So this we will be discussing in the next discussion. Thank you very much. Stop here.